Hello everyone, and welcome to another video in a series dedicated to engineering thermodynamics. Today's topic is the first law analysis of closed systems. I will start the discussion by defining the moving boundary work. Then I will introduce different processes. Next, I will discuss the actual energy analysis of a closed system. And finally, I'm going to talk about specific heats, what they are, and how they would help us with energy analysis of closed systems. Okay, so let's start with the moving boundary work. Imagine a system containing a piston and cylinder like this. Now the boundaries of if we add heat to our piston and cylinder, the system starts to expand and the piston will move to a new position. Let's say here. The piston has moved for a distance of ds. From definition, we know that delta work is force times ds, or displacement, right? I'm showing work with delta because we are talking about work, which is a path function. And I'm going to add a subscript b to w to indicate that this equation is for the boundary work, or the work that this moving boundary is doing. Our boundary was here, and then it moved up to there. The work that the boundary does is shown by delta W. We also note that the force acting on this piston, moving it upward, is actually the pressure inside the cylinder times cross-section area of the piston. So let's write that down here. If I combine these equations, I will get delta WB, or delta work of boundary, is pressure times cross-section area of the piston times ds. Now, cross-section area times ds actually represents this volume. So this equation can be rewritten as P d volume. If I make an integral, I will get the boundary work of a process going from state 1 to state 2 is actually the integral from 1 to 2 of P d volume. This is the moving boundary work, or simply boundary work. Now let's take a look at the equation that we have from a PV diagram perspective. So the boundary work is integral from 1 to 2 of pressure delta volume. And if we look at the PV diagram, if this is the process from state 1 to state 2, the boundary work is the area under this curve. Because this red area is actually the integral of P d volume. This is actually very helpful because sometimes in problems we deal with processes that are actually very straightforward, and we can calculate the area underneath the curve rather easily. Now, as we know, work is a path function. So if we have, again, a PV diagram, and this is our state 1 and this is state 2, then based on the path that we take, the boundary work will be different. So if we are taking the purple process, this will be the boundary work. If we are taking the green process, then this will be the boundary work. And if we are taking the red process, then this will be our boundary work. Now, as you can see, the boundary work of the purple process is not equal to boundary work of the green process, which is not equal to the boundary work of the red process. Now, if we are dealing with a cycle, then this will be our PV diagram. We start from state 1 and go to state 2 from this path, and then come back from this path. So this is a cycle, right? Now, the net work or net boundary work is equal to the boundary work from 1 to 2 minus the boundary work from 2 to 1, right? Now the boundary work from 1 to 2 is this much. Boundary work from 2 to 1 is this much. So the net work is the black area. This will be the net boundary work. So again, these are graphical representations of the equations that we deal with, and they can prove helpful with certain problems. Now let's introduce some processes. So the first process that we want to talk about is a constant volume process. Now the boundary work is the integral of P dV, right? Now a constant volume process means that volume 1 is equal to volume 2, meaning dV is 0. Now we can readily conclude that the boundary work in a constant volume process is 0, because no change in volume means 0 work. I can draw a PV diagram and look at this constant volume process from a diagram perspective. So if this is our PV diagram, a constant volume process looks like this. Now a vertical line does not have an area on the curve, right? So boundary work will be 0. Okay, the second process that we want to talk about is a constant pressure process. We sometimes call a constant pressure process an isobar process. So if you encounter the word isobar anywhere, it means constant pressure. Okay, so again, boundary work is the integral of pressure delta volume. Now in a constant pressure process, P or pressure is constant. Now because it is constant, it can come out of the integral, meaning the boundary work is pressure integral of the volume from 1 to 2, which is P delta volume. So in a constant pressure process, the boundary work is pressure delta volume. Let's draw the PV diagram to get a visual perspective. We are going from state 1 to state 2 in a constant pressure process. Now, by definition, the boundary work is the area under the curve. Now, this is a rectangle, and you know that the area of a rectangle is this side times this side. Now, the vertical side is the pressure. The horizontal side is delta volume. So the boundary work is P delta volume. Okay, the third process is isothermal process. Now, isothermal process means that the temperature is constant. So again, boundary work is the integral of P d volume. Now, a constant temperature process on itself does not give us a relation between the pressure and volume, right? It can be anything. But let's narrow it down to ideal gases. There, we have an equation between pressure, volume, and temperature, and we can use it to calculate this integral. So let's narrow down the process that we are interested in to ideal gas only. Now, for an ideal gas, we know that pressure specific volume is R gas constant times temperature, or pressure volume is the mass of the gas times the gas constant times temperature. Now, if we are talking about closed systems, so the mass is not changing. The process is isothermal, so the temperature is not changing, and the gas constant is always the same for a specific gas. So the right-hand side of this equation is a constant. always. I'm going to show it with letter C. So I get that pressure times volume is a constant C. If I play with this, I'll get that pressure is C over volume. Now this is a function. It shows the relation between pressure and volume. I can plug in this equation back into the definition of boundary work and make that integral. So the boundary work is integral of constant C over volume dV from state 1 to state 2. Now C is a constant, it can come out of the integral. So we are talking about the integral from 1 to 2 of d volume over volume. Now the answer to this integral is actually the natural log. So we are looking at C natural log of volume from state 1 to 2, which is C natural log of volume 2 over volume 1. Now remember that C is actually pressure times volume. And any state during this process, pressure times volume is the constant C. So I'm just going to say C is pressure initially times volume initially. So P1 V1 natural log of volume 2 over volume 1. Now the boundary work for an isothermal process for an ideal gas is P1 volume 1 natural log of volume 2 over volume 1. Okay, next up is polytropic processes. During the actual expansion and compression processes of gases, pressure and volume are often related by an equation in the form of pressure volume to the power of n is equal to C, a constant. Okay, in this equation, n and C are constants. Now, a process like this is called a polytropic process. Let's see if we can calculate the boundary work for a polytropic process. Playing with this equation, I get pressure is C times volume 2 minus n. I also know that the boundary work is integral from 1 to 2 of P dV. I can plug in everything here and say integral from 1 to 2 of C V minus n dV. Now the answer to this integral is C V to power of 1 minus n over 1 minus n from 1 to 2, which is C V2 1 minus n minus C V1 1 minus n over 1 minus n. Now remember, C is P times V to power of n, which is P1 V1n or P2 V2n. So I'm going to plug in P2 V2n here and P1 V1 here instead of C. And if I do that, I'll get that the boundary work is P2 volume 2 minus P1 volume 1 over 1 minus n. Now, the only condition for this equation is that n cannot be 1. Because if n is 1, then the denominator will be 0, and that is not acceptable. Okay, so I just moved up boundary work equation here. And now let's assume that the gas that we're working with is actually ideal gas. Now, if we're dealing with an ideal gas, pressure times volume is mass of the gas, gas constant, and temperature. So combining these two equations, I get the boundary work in a polytropic process for an ideal gas is mass, gas constant, temperature final, temperature initial over 1 minus n. for the cases that n is not 1. Now, for the case that n is actually 1, the process is P is constant over volume. Now, this is the case of an isothermal process. This was an isothermal process for an ideal gas that we covered a few pages ago. And we already know that the boundary work for this scenario is pressure volume 1 natural log of volume 2 over volume 1. So a polytropic process with n equal to 1 is actually an isothermal process for an ideal gas. If n is not equal to 1, the general equation to find the boundary work is here. And if we are dealing with an ideal gas, the equation will reduce to this one. All right, we can start to talk about the first law analysis of a closed system. Okay, the general equation for the first law analysis of a closed system, we know it from before, is that all the energy coming in minus all the energy going out is equal to the change of energy of the system. And the unit will be kilojoules. We have a per unit mass form of this equation, which says small letter e coming in minus small letter e going out is equal to change of small letter e of the system. And the unit will be kilojoules per kilogram. And in the rate form, we have the rate of energy coming in minus the rate of energy going out is equal to the rate of change of energy of our system. And the unit will be kilowatts. And more commonly, this equation is written in the form of Q net minus W net is equal to the change of energy, or in the rate form, Q dot net minus W dot net is the rate of change of energy of the system. Now, Q net was defined as Q coming in minus Q going out. W net, on the other hand, was defined as W out minus W in. Now, W is actually representing all of the works that can cross the boundary of our system. It can be a shaft work, it can be electrical work, and it can be the work of the moving boundary or the boundary work. So keep that in mind. Now, when dealing with a system, it is very important to take a few things into account. First, you need to define your system using boundaries. For example, in this piston and cylinder, the red line is the boundary. Now, if the piston moves, the boundary also moves with it, and hence the work of the moving boundary. Now, defining the boundaries is step 1. Step 2 is to define energy interactions at the boundaries. So, are there any heats coming in or going out? Are there any other form of work coming in and out? Is one of the boundaries moving? Is this boundary going to move up here? Is any boundary work involved? You need to figure them out. So step 2 is define energy interactions at boundaries. Now, after these 2 steps, we can write down the equation in the form of Q net minus W net is equal to the change of energy of our system. These 2 steps are actually for the left-hand side of this equation. We need to define the boundaries so that we can define the energy interactions. Now, work and heat are energy interactions at the boundary. Anything else happening is inside the system and should be considered in the change of energy of the system. What I mean by that is, let's assume inside this piston and cylinder, we have ice, which is melting into water. Now, the process of ice melting into water does not interact or cross the red boundaries. So it's not related to the left-hand side of the equation. It is not included in the heat or work interactions. It is included in the change of energy of the system. So ice melting to water should be included on the right-hand side of the equation and not left-hand side of the equation. You'll see what I mean when you try to solve some problems. Another important thing that you need to pay attention to is that whatever interaction happens on the boundaries happens between the system and the surroundings. Okay, so if the system is having a positive Q net, meaning that the system is gaining heat, it means that the surroundings is losing heat. The same can be said for work too. When the system has a positive work interaction at a boundary, means that the surrounding has a negative work interaction at the same boundary. Okay, for example, here when the system expands and we have boundary work in the form of piston moving up, the surrounding receives the same amount of boundary work in the form of compression, because the air in the surroundings is actually being compressed when the piston is expanding. Okay, so at boundaries, at system boundaries, every interaction happens between the system and the surroundings. Okay, so Q net minus W net is delta E of our system, right? Delta E, if you remember, is actually delta internal energy plus kinetic energy plus potential energy. Now I'm going to drop the nets just to keep it simple and say Q minus W is delta capital U kinetic energy, potential energy. Now the work itself can have many forms. So it can be maybe shaft work, it can be boundary work, or it can be electric work, or any other form of the work. So Q minus all these W's is still equal to delta capital U, delta kinetic energy, plus delta potential energy. Now, in the special case that we are dealing with a constant pressure process, then I know that the boundary work is P delta volume, right? Now, if the system does not have any kinetic or potential energy changes, then I can neglect these, and then I can rewrite that equation into Q minus W. I'm taking Ws and W electric together as W is equal to delta internal energy plus boundary work, which is P delta volume. Now delta U plus P delta V is actually delta enthalpy. So in a system where we are having a constant pressure and we can neglect the kinetic and potential energies, Q net minus W net, not including the boundary work, is equal to the change of enthalpy of the system. Now, please pay attention that you cannot include the boundary work twice in the same equation. When the right-hand side of the equation is in the form of change of enthalpy, it means that we have included the boundary work on the right-hand side of the equation. If the right-hand side is in the form of delta U, or the change of internal energy, then it means that you have to include the boundary work on the left-hand side of the equation inside the work, inside the net work term. Okay, so you have to include the boundary work, but only once, either on the left or on the right-hand side of this equation. Another special case is when our system is expanding against the vacuum. Now, in many problems, you will see scenarios like this. We have a rigid tank, which is divided to two by a thin membrane. And on one side, you have a system with a pressure and a temperature and everything. And the other side is vacuum. And then the problem says that the membrane is suddenly removed. And they ask you to do a first law analysis on this problem. Now, One thing you need to pay attention to is that, okay, our system was initially like this, and then after the membrane is ruptured, then the system expands to the green line, right? Now, naturally, you would say, okay, the red boundary has moved to the green boundary, so we have a boundary work involved. The answer actually is that there is no boundary work involved in problems like this. Now, I know that the red boundary has moved to the green line, and you would expect a boundary work in the form of integral of pressure times dV. But remember one of the points that I made a few pages back. Every energy interaction needs to happen between the system and the surroundings. Now, when this membrane is ruptured, when this membrane is removed, the gas starts to expand, but there is no work involved because there is no surroundings on the vacuum side. We don't have any mass here. So if work is moved across the boundary in the form of boundary work, something on the right-hand side, something in this empty side of the tank needs to receive that work. Some sort of surroundings is needed to receive the work to make the work interaction. But because the vacuum is empty, because there is no mass there, because there is no surroundings in the vacuum, no boundary work is happening. So this is very important because you will see this in many examples and maybe in your exams. So when the membrane is removed and the system is allowed to go into a free expansion into vacuum or against vacuum, no boundary work is happening. So when you write down the Q minus W is equal to delta E, which we can safely neglect the kinetic and potential energies here, so delta internal energy, there is no work, and if the system is well insulated, there is no Q as well, and you would get that the internal energy after the expansion is equal to the internal energy before the expansion. So the internal energy of the system does not change if the tank is insulated. All right, we can wrap this video up by the topic of specific heats. Now, specific heat is the amount of energy required to rise the temperature of a unit mass of a substance by 1 degree. Now, generally speaking, the amount of energy required depends on how the process is executed. Now, we have two different type of specific heats. One, we show it with C of V, is the specific heat of constant volume, meaning the process of heating is constant volume, and Cp, for the specific heat of constant pressure, meaning the process of heating is constant pressure. Now, generally speaking, Cp is larger than Cv. The reason for that is during the constant pressure process, some of the energy added to the system is used to raise the piston to keep the pressure constant. In other words, some of the energy is used for boundary work. Let's take a look at the specific heat using the first law analysis. For a constant volume process, I can say the amount of energy coming in minus the amount of energy going out of the system in a constant volume is equal to the change of the energy of the system. Now, neglecting the potential and kinetic energies, that will be the internal energy only, right? Now, I'm trying to find the amount of energy that is needed to change the temperature by 1 degree. So delta energy coming in minus delta energy going out can be written as specific heat of constant volume times dt, the amount of energy, is equal to du. This gives me Cv is actually du over dt at constant volume. So let's write that down here. Cv is actually du dt at constant volume. I can write the same thing for the constant pressure. I can say the amount of energy needed, which is Cp dt, minus the amount of energy required to move the piston, or the boundary work required to keep the pressure constant, is equal to change of internal energy, which gives me Cp dt is du plus pdv, right? Now du plus pdv is actually the enthalpy. So Cp is actually the enthalpy dt at the constant pressure. Let's write that down here. Now, writing these equations in this form gives us another perspective. We can define Cv as the change in the internal energy of a substance per unit change in temperature at constant volume, and we can define Cp as the change in the enthalpy of a substance per unit change in temperature at constant pressure. Now, as you can see, because Cp and Cv are defined as a relation between system properties, see, Cv is du over dt. Both are the properties of a system. Cp is dH over dt, which again, both are properties of the system. Now, because they are defined by properties of the system, they too are properties of the system. So Cp and Cv both are properties of the system. Now, because they are properties, they are independent of the process, just like the internal energy is independent of the process and is only dependent on the state. Cp and Cv are also independent of the process and only dependent on the state. Now, we used constant volume and constant pressure states to define these two, but they are actually independent. Regardless of how your substance reaches state 1, Cp and Cv at that state 1 is always the same. Now, both Cv and Cp have the same unit in SI, that is kilojoules per kilogram Kelvin. Generally speaking, both Cv and Cp are functions of both temperature and pressure of the substance, and we have tables to read Cv and Cp form. Okay. But what happens if we are dealing with ideal gases? So for ideal gases, we have this equation: pressure times a specific volume is gas constant times temperature, right? We also have the equation that enthalpy is internal energy plus P specific volume, right? If I plug in the ideal gas equation here, I get enthalpy of an ideal gas is internal energy of the ideal gas plus gas constant times temperature. Okay. Now, for ideal gases, internal energy is a function of temperature only. Now, generally, for substances, internal energy is a function of temperature and pressure, but for ideal gases, in the range of low pressures, low densities, and high temperatures, internal energy of an ideal gas is a function of temperature only. Now, because this is a function of temperature only, and R times temperature obviously is a function of temperature, enthalpy of an ideal gas is a function of temperature as well. So for ideal gas, both enthalpy and internal energy are functions of temperature only. Now remember the definition of a specific heat. Cv is the internal energy dt at the constant volume, right? Now for an ideal gas, U is a function of temperature only. So I can play with this equation and say du is Cv dt. If the internal energy is a function of temperature, then the specific heat at constant volume is a function of temperature at most. Okay, so this will be du is Cv, function of temperature, dt, right? The same can be said about Cp. Cp is the enthalpy dt, constant pressure, which can be written as the enthalpy is Cp as function of temperature dt. And when we want to make the integrals, we will end up with delta u is the integral of Cv dt, delta h is the integral of Cp dt. Now, there are different ways to make this integral. We can take Cp and Cv as constants in a reasonable range of temperature. We can go to some tables and read Cv and Cp. As I said, there are properties of a system at different temperatures, and maybe make an average between the initial and final temperature of our system. There are functions, more complex functions, that relate Cv and Cp to temperatures. We can plug in that complex equations into these integrals and make the integral. But for the sake of simplicity, during these lectures, during these videos, I'm going to take both Cv and Cp at constants during the processes in the problems. Okay, so I'm going to bypass these integrals and just say delta U is Cv delta T and delta H is Cp delta T for ideal gases. Okay, back to our previous equation. Now for ideal gases, we found that dH is du plus r dt. So plug in the Cp and Cv into this equation, we get Cp dt is equal to Cv dt plus r dt. Now I can cross the dt's and get that the Cp of an ideal gas is equal to Cv of the ideal gas plus the gas constant. Now this is a very important equation. We also define a new property in the form of a specific heat ratio, and it's the ratio of Cp to Cv. We sometimes show it with small letter k, sometimes show it with a small Greek letter gamma. Depending on the book that you're using, you may encounter either of these. Okay, we discussed ideal gases, but what happens when we are dealing with liquids and solids? Now for liquid and solids, because their specific volume or the density does not change, the constant volume and constant pressure of specific heats are identical, meaning that C of V is equal to C of P. We show it with C only. Now when trying to calculate the internal energy, we can use the equation du is C dt. And assuming that C is a constant, we get that the change of internal energy of a liquid and a solid is C delta T, or Ct2 minus T1. Now, for enthalpy, things are a little different. Now, the equation for enthalpy is H is equal to U plus P specific volume. I'm going to make a derivation and use the chain rule. I get dH is du plus pdV plus v dp. Now in solids and liquids, as I mentioned before, specific volume really doesn't change. So this guy is out. Now it depends on what kind of process the system is going through. Process type 1 is when the system is going through a constant pressure process. This means that dP is 0, meaning dH is equal to du. It means change of enthalpy of the system is equal to the change of internal energy of a system. Now, an example for a constant pressure process is boiler or heater. The second process that may happen is an isothermal process or a constant temperature process. Now, this means that the change of internal energy is 0, because if the temperature is not changing, the internal energy of the system is not changing. This means dH is equal to specific volume dP, meaning the change of enthalpy is specific volume delta P, or specific volume P2 minus P1. Now, an example for this case is when we are dealing with a pump. Now, pump usually does not involve any temperature changes, because usually the process is adiabatic and no heat is coming in or out of the system. So the change of enthalpy of the liquid is equal to the specific volume times the change of pressure across the pump. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like, as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again, and see you in another video.